Okay, in this example, we're going to deal with a case where we have acceleration. And we're also going to add friction, just to keep it interesting. One last thing is I'm not giving you any numbers in this problem. I know that that's going to make you sad. But I want you to try to get comfortable with manipulating your equations algebraically without numbers in them. This actually saves you a lot of time if you make a mistake, because you can go back and check your algebra without having to continually punch in the numbers to see if you made a mistake calculating some quantity by multiplying two numbers together. That can get rather tiresome and it's a lot of work. So this is like eating your vegetables. It's really actually good for you, and I think you should try it. So here's our scenario. We have a mass connected to another mass on a flat surface, but one is hanging. It's connected by a rope hanging over a pulley, and for now, our pulley is frictionless. We might not really know what that means, but what it does mean, a consequence of that, is that the tension in the rope in both pieces, both here and here, are going to be the same. Eventually, as we get along in further chapters, we'll have a situation where there is some resistance to the rotation of the pulley, keeping the two tensions in the ropes different. We have to make sure that we understand right now that that's not the case, that the tension in the rope is the same everywhere. Otherwise, we actually have too many unknowns and we won't be able to solve the problem. Now, the other thing that we know in this problem is we are told that there's friction between the surface, the flat surface, and the mass that's sitting on it. We know that because we've been given the coefficient of kinetic friction, mu sub k. We also know that the mass 2 is bigger than mass 1. It's big enough so that everything is going to accelerate in the direction shown. That is, mass 1 is going to accelerate in the direction you see, and mass 2 is going to accelerate downward. Given the fact that we know these three quantities, so when we're doing our algebra, we'll treat them like we know that what numbers they are. We need to find the tension in the rope and the acceleration of this system. We're going to be using F equals ma. And because we have two masses, we're going to have to look at the forces for both masses. So let's start with mass 1. Now, because mass 1 is accelerating horizontally, I know the x forces are going to be adding up to mass times acceleration, but in the vertical direction, mass 1 is not moving. So those forces will add up to be 0. Can we identify what the forces are that are acting on mass 1? Well, here's some easy ones. There's gravity, and there's a normal force. I'm going to call it N1 to represent the fact that it's associated with mass 1. Even though I don't have another normal force in this problem, I think it's a good practice. Notice also, I was careful to write M1G, not just mg. There's two masses here, and if I don't label them, I'm going to get all confused. The rope is going to pull mass 1 in this direction because ropes can't push. And because we already know that the object is moving in this direction, the frictional force has to act in the opposite direction. I've labeled all the forces acting on mass 1. Let's look at this expression. So I'm going to have tension is in the positive direction and friction is in the negative direction. And that's going to be given equal to m1a. It's really important that you realize that when I wrote this, I took into account that the acceleration and the tension are in the same direction, and so they have the same signs. I don't ignore the vector nature of the acceleration when I get over to the right-hand side of the equation. That I have to pay attention, otherwise you get the wrong answer. Now, I also learned that the frictional force is equal to the coefficient of friction times the normal force. Now, I don't know what the normal force is yet, but I can find it if I look at the forces acting in the y direction. I have the normal force and the weight, which act in opposite direction. The normal force is up, so it's positive. The weight is down, so it's negative. Those are the only two vertical forces I have on mass 1. And so these two things have to add up to be 0. The mass is not moving in the vertical direction, so the forces add up to be 0. That means that that normal force is equal to the weight. Here's a situation where it is. I can put this in here. Okay, now I'm done with mass 1. Let's move on to mass 2. Mass 2 only really has things going on in the vertical direction, so it's saving me a little bit of trouble because I only have to work with this expression of Newton's second law. The forces in the y direction equal the mass times acceleration in the y direction. What do I have? I have the tension in the rope is acting on mass 2 and its weight. Okay, those are the only two forces. Let's put them over here. I like to keep my normal sign convention that up is positive and down is negative. And so the tension is a positive force, but the weight is a negative force. But now this is where I have to be really careful. When I write is equal to m2a, I have to take into account that this acceleration is downward. That's the negative direction. So I want to write this, not only do I want to, I need to, as minus m2a. If you forget that negative sign, you will get the wrong answer. You can't get the right answer unless you do another mistake along the way. Another option that you might see that's used in some books is for when an object is accelerating downward, they make that the positive direction. That would then switch these two terms. The weight would be positive and tension would be negative. It would really be like multiplying that whole expression by -1. All right, so what we're left with at this point are these two equations that I'm going to put in boxes. This is where I say you're done with physics, because now I have two equations and two unknowns. I want to solve for tension and acceleration. How I do that is really related to how I would solve an algebra problem. We're all going to have our ways that we prefer to do this. I do too. Some ways are harder than others. I'm not going to do it hard. So in these scenarios, what I find really easy to do is I could solve both of these expressions for tension and set them equal to each other. For instance, T here is equal to m1a plus mu sub k m1g. And over here, T is equal to m2g minus m2a. Now, I'll set T equal to T, and I get m1a plus mu sub k m1g is equal to m2g minus m2a. Now, I'm going to solve for a, because that's the only unknown that's left. I've gotten rid of the tension. So I'm going to put all my a terms on one side and everything else on the other. So I'm a little bit out of the frame here. I'm going to just rewrite this a little higher so you can see it. There you go. So I find an expression for the acceleration And I want you to look at it and think about it because there's something about it that's relatively important. If we look at the top term and we think about Newton's second law, we know that acceleration is equal to the force over the mass. And the top term really refers to, for the system, all the forces that are acting along the line of the acceleration. That might be confusing because it sort of changes direction depending on which mass you're looking at. But if I sort of think of that as a continuous line, the weight of mass 2 is tending to pull the system down in the direction of acceleration while the frictional force is working against it. And all this is the frictional force right here. And then the total mass of the system, which we're dividing by, is m1 plus m2. So this actually makes a lot of sense. Once I know that acceleration, I can take it and substitute it into either one of these expressions and find the tension. Of course, I should find the same tension if I use this expression or this one. That might be a good way to check your work. So once again, there's a lot of things in this example that I hope you pay attention to. How I work with friction, how I work with the signs when I'm looking at F equals ma, and also the idea of being more comfortable with not substituting in numbers until I've done all my algebra. If I solve this problem the way I did and then I put all my numbers in this last step, that would be the only calculation that I would have to check with my calculator, and everything else I could just kind of go through and make sure that my algebra was correct. So I'm a big proponent of this. Let's see if you can take that on.